we are looking at the shapes of orbitals. Remember that the shape of an orbital is used in describing the quantum numbers of an electron. So the shape of an orbital also helps to specify the characteristics of an electron in terms of size, shape, orientation, such that no two electrons can have the same four quantum numbers, and as such we differentiate our electrons as well by also looking at the shape of the orbital the electron is found in. Now I want to start with my s orbital, and we are going to take down a definition for an s orbital by also defining the term orbital in our definition. So we have described an orbital as being a space, right, which represents the highest probability, right, a space which represents the highest probability of finding an electron right, in three-dimensional space or whatever, right, or in 3D. Right, I could just leave this out because I already said space before. So I've defined what is orbital in my definition, and instead of just saying it's a space, I'm going to describe the shape of the space. So we are saying it's a spherically symmetrical space which represents the highest probability of finding an electron. Now this big term here is spherically symmetrical. I'm going to draw what the shape of the orbital will look like, and this is what you're expected to draw in the exam. So it's spherically symmetrical, so that's a circle, and I want to draw the 3 dimensions because we're saying it's symmetrical about the nucleus. So you're going to think of it as being spherical about the nucleus, where the nucleus is where the 3 axes cross. So we have X, this is X, Y, Z, I believe. I could be wrong. Right, so X, Y, Z in some direction here. X, Y, and Z. Here we go. That's miss you are wrong. X and Y being perpendicular. There we go. So this is my s orbital, or the drawing of my s orbital. And in addition to knowing a definition for the s orbital, you should also be able to describe the shape. So I'm describing it as spherically symmetrical about the nucleus. Right, so this is our shape of our orbital. Right, so if you're asked to describe the shape, and where we asked to describe the shape, we are also asking for a diagram. I'm also going to include in here a term called a node, and I'm going to write what the node is. A node represents, and it's a space, right? It's a space of 0 probability of finding an electron. So a node represents a space of 0 probability of finding an electron. And if we are saying our s orbital is spherically symmetrical about the nucleus, would you ever be able to find an electron where the nucleus is? No. So in describing the shape of the s orbital, I'm saying that it's spherically symmetrical about the nucleus, and this is where the nucleus is a node. Now in my diagram, I have shown that the s orbital is spherical in shape. So does this mean that every s orbital found in the first shell, the second shell, the third shell, are they all the same size spherically? No. We are saying that if I have a 1s orbital versus a 2s versus a 3s, this would be the shape of my 1s orbital. And for an orbital in the s orbital in the second shell, we are saying that the probability of finding the electron is in a larger volume of space. For the 3s subshell, which contains the s orbital, we are saying the probability of finding the electron is in an even larger region of space. Remember that an orbital is a volume of space around the nucleus, which represents the highest probability of finding an electron in three-dimensional space, right? In this three-dimensional space, we describe the position of the electron in terms of probability or electron density. Of course, in our 3s orbitals, right, we're seeing a larger volume of space where we have a higher probability of finding our electron. But remember that at the center of our orbitals, we would find the nucleus, where the nucleus is a node, which is a zero probability of finding the electron. I also want to just draw in my diagram. We don't just draw a circle with a dot to represent the node. I must draw in my axes. Right? I draw in my axes in my diagram as well. Right, so these are the basic shapes of 1s, 2s, and 3s s orbital, where we see an increasing region of space to find an electron in a higher energy level. Let's take a look at the p subshell, or the p orbital, I should say. And we want to look at a definition for p orbital, as well as the drawings used to describe the p orbital. So I'm going to define the term orbital, and in order to describe the p orbital, I have to describe its shape. So we are saying the p orbital is a dumbbell shaped region of space which represents the highest probability, right? And I'm going to use a term used in the textbook here, which represents the highest probability of electron density, right? Remember, the electron is a cloud, right? So it's a charged cloud, a dense cloud, right? So we're saying there's a p orbital which has a dumbbell shape, and in this dumbbell shape, this is our highest probability of finding our electron. So I'm going to go ahead and draw my dumbbell shape. right? And in order to do so, I'm drawing my 3 axes because the p orbital is arranged around each axis, right? So this, let's say this is my x-axis. This is one p orbital. If I have a y-axis, we have another p orbital. Where I have my z-axis, we have a third p orbital, right? They're all meant to be the same in shape, right? So excuse my drawing. Into each drawing, I'm going to include the other axes for reference. I'm just going to draw them in. We are saying that the p orbital is a dumbbell-shaped region of space, or a dumbbell-shaped orbital, right, which represents the highest probability of electron density. So we have in a p subshell, or in every p subshell, you're going to find 3 p orbitals. Right, so I'll make sure and include that here. Right, so in each p subshell, there are 3, and I want to leave a space for a word here, 3 p orbitals. Right, there's a term used to describe a p orbital, or these different orbitals that all belong to the p subshell, and this word is called degenerate. Right, the word degenerate means they are the same energy. Right, so we say that degenerate orbitals are of equal energies. So we have 3 degenerate p orbitals in a p subshell. And our 3 p orbitals we can now differentiate from each other. So instead of just calling this p orbital, this is a p orbital, this is a p orbital, we can differentiate them by the axis or axis that they lie on. So this is px, py, and a pz orbital. So this means if I go to my energy level 2, where there's a 2p subshell, this means I'm going to have a 2px orbital, a 2py, and a 2pz. If I go to energy level 3, where the p subshell is identified by the quantum number 3, my 3p orbitals would be 3px, y, and z. Right, so each shell may contain a different number of subshells. Where a shell contains a p subshell, each p subshell is made up of 3 p orbitals. The 3 orbitals are equal in energy, and what that term equal in energy means, they're also going to be equal in terms of their shape. Right? The only difference between one orbital to the other is the orientation. Right? You are to know how to draw your 3 p orbitals with the axes, and be also able to label them px, y, and z. I'm also going to describe the shape of one by including a little description. So we say it's dumbbell shaped, right, about the nucleus. And you're going to mention here that the nucleus is what we call a node, right? So that's why compared to what's in the textbook, the node represents a 0 probability of finding an electron in space.